So last time, yeah, we had the problem-solving exercises. So I thought to maybe change the schedule around a little bit. So we will continue that, but maybe either the last session today or the first one tomorrow, depending on kind of how fast my lectures go. So maybe just to kind of briefly review where we're at. So in the first lectures, I introduced this chiral waveguide model. So it's this abstract 1D system where light can propagate in one direction and couple to atoms in the waveguide. I introduced, in principle, the full Hamiltonian. That includes both the atomic and field degrees of freedom that describe the system. And then I argued that one of the kind of potentially big simplifications is to realize that the field is not an independent degree of freedom. So you can actually integrate out the fields. So then you find that the total fields consists of what you send in. Plus a component that's rescattered or emitted by the atoms. And then, so the message of this equation is that if you know what you send in, and you know what the atoms are doing, you know the atomic dynamics, then you can go and reconstruct any correlation function of the field for free. And then the atomic dynamics themselves are governed by an effective non-Hermitian Hamiltonian, which can include some driving term, so the effect of the field you send in. Plus what looks like now is effective spin interaction. Where atom J can go from the excited state to the ground state, atom I will go from the ground to the excited state. Physically, that's due to the emission of a photon and reabsorption. And then this kind of Green's function here just describes how a field propagates from one atom or one point to another. So in the chiral waveguide, we had that this was proportional to a step function, right? Because fields only propagate to the right. An atom to the right can see an atom on the left, but not vice versa. And then in 1D, you also pick up a propagation phase of e to the I k naught d, where d is the distance of propagation. So the interesting, and again, remember that this is a non-Hermitian Hamiltonian. So you should think of this as a shorthand for a full master equation. And I'm just not writing the master equation because it's faster to write this. And then my claim as well is that even though we kind of rigorously derive this for a waveguide, this should be true in general. So if I go into free space or a cavity or anything else, all I have to do is put in the proper Green's function that describes how photons propagate in that particular electromagnetic environment. And so, it's a kind of very different way to view quantum optics, because what you're literally saying is, forget about the fields. The hard part of the problem is solving what looks like some kind of driven and dissipative spin model. Okay? So the goal of the next lecture is to kind of understand what are the implications of mapping quantum optics onto this type of spin model. So at the very beginning of the first lecture, what I tried to convince you, or my claim was that if you use the spin model properly and you understand all of its consequences, in principle it includes wave interference and multiple scattering of light, and then you can actually try to use that in protocols. So if you want to build a photon-photon gate or a quantum memory, that there's actually ways to do that with errors that are exponentially smaller than what textbooks would have predicted. Okay, so if that's true, then that's indeed a very kind of powerful statement. So I will talk about kind of these protocols, but I thought it was also important to maybe understand what the original textbooks say and why they're wrong. So hopefully that'll give you a better appreciation of this spin model in the first place. Okay. So that's going to be the point of this lecture. So the textbook. If you want the formal name, the formalism is called Maxwell-Bloch equations. So that's just the kind of conventional way that you describe atoms interacting with propagating fields. So I'd like to talk now about the textbook and why it's wrong. So the Maxwell-Bloch equations were historical attempts to understand atom-light interactions in free space. But in a kind of rather specific set of circumstances. So in particular, you might have some kind of collection of atoms in free space, in a three-dimensional free space. And typically what you do in a quantum optics experiment is you shine in light in a mode that you control. So for example, you might create a Gaussian beam, send it into the atoms. And then on the other side, you would have some collection optics to also collect the same Gaussian beam. So again, the problem in optics is you don't really know how to collect light going into all 4 pi. So here you can put in lenses and detectors and so on. So what you're really trying to ask is, what's the effect of the atoms only on the Gaussian beam that you send in? Okay, so the atoms could scatter light into other directions, but that light is assumed for practical purposes to be lost. Okay, so your goal is to kind of detect or predict what's the effect only on the Gaussian beam as it propagates through. So the thing about the Gaussian beam is it's a quasi one-dimensional field, right? You can write down a Praxeal equation or a quasi one-dimensional equation. So this is a quasi 1D propagating mode, where the dimension is basically defined by the direction of propagation. And so then it turns out that basically the model that people wrote down, so the Hamiltonian that people wrote down for this Gaussian beam, is exactly that of the chiral waveguide. So back then when they invented it, they had no idea that there was actually a thing as a chiral waveguide. But kind of made by historical accident, the equations they wrote down happened to be exactly the same. Okay. So the point is that this Gaussian beam propagation, you basically can mathematically map to the chiral waveguide. And then the only other thing which we didn't discuss in the chiral waveguide so far is, in free space we have this notion that atoms can still emit into other directions. Okay. So the other directions, you have to model that somehow. And the assumption was basically that if an atom is excited, then it'll spontaneously emit independently of what any other atoms are doing. Okay. So if we call this Hamiltonian, just to be concrete, the effective Hamiltonian of waveguide QED. Yep, sorry. Exactly.
As we're kind of having this beam waste, and then there will be like some minimal standard deviation. So like, is there any like functional dependence of that, like with the direction of propagation, or?
Yeah, right. So let me check if this is what you're asking. So a real Gaussian beam, the Gaussian beam you can describe, so there's one component that has basically, that looks like a plane wave, e to the I kz. You also have a kind of transverse profile, so atoms in the middle, on axis, they couple more strongly than an atom at the very edge. A true Gaussian beam also has a spherical phase front, which is described by a so-called gooey phase. So that would be the kind of proper description of a Gaussian beam. So the kind of so it is possible to fold all those effects still into the chiral waveguide model. So for example, if it's like if you have one atom that's kind of off to the side and it couples more weakly, you could, if you want, kind of introduce an extra position dependence of this gamma 1D, which describes your coupling to the 1D mode in the first place. So it turns out that if you want to get the qualitative physics, you don't really have to worry about that. You can just say that the chiral waveguide, forgetting about all that extra 3D stuff, it still produces the kind of essential physics. So we'll focus on that simplified version. Okay. So then, effectively, so then basically it turns out that the effective Hamiltonian for the Maxwell block equations is exactly the same as that of chiral waveguide QED, plus this one extra term. The attempts to model the kind of additional emission into 4 pi. Okay, so this is a non-Hermitian or anti-Hermitian term. It purely describes dissipation. And the fact that it's just a sum on I, rather than a sum on pairs, that says that each atom effectively sees an independent bath. So if that atom is excited, it's going to emit at a fixed rate, gamma naught, irrespective of what any other atoms are doing. Okay, so that's basically the Maxwell block equations. Sorry, just to make my notation consistent, I'll call this kind of bad emission gamma prime. Okay. So I should say that when I write the effective Hamiltonian this way, it's a little bit of a hybrid model. Okay. What I mean by that is historically, people didn't know that they could integrate out the field. So the Hamiltonian that they worked with was actually this full Hamiltonian, including the field degrees of freedom explicitly, and with this extra independent emission built in. So they were really trying to solve some kind of field theory model. So here I'm using a little bit of kind of hindsight, right? So 40 years after they invented it, now we realize you can integrate out the field. So I'm going to adopt this kind of hybrid approach where I try to solve a spin model, with this extra kind of independent emission built in, knowing that it reproduces the same answer as what you would get if you kept the photons in from the very beginning. And I do that just because, since the point of the lectures is really to deal with the spin model, I think it's more convenient to deal with the spin model from the very beginning rather than just kind of solve the wave equations for no particular reason. Okay, so I just want to make that clear. This is not what you would see in a textbook, but it's mathematically equivalent. It's also wrong, because my whole point is to show that this independent emission term here gives rise to a lot of bad stuff that's not actually fundamental. Okay, so the goal of this lecture will be to solve a model that we know is wrong, just so we can later appreciate better why it's wrong. Okay, so at this point we should also, all right, so maybe the first thing we can do is solve for just a single atom. Okay, that's the simplest problem. So we did that already for the pure chiral waveguide model. We saw that if I only have a single atom, all the light has to transmit, and then on resonance, the light picks up an extra pi phase shift. So now we basically want to go and revisit that same problem, but now allowing for the fact that when an atom is excited, it can also emit a photon at a rate gamma prime into directions that we can't see. Okay. So to do that, we just have to, we take this effective Hamiltonian, and we also have to specify the driving. Sorry. So we want to send in light, and the type of light we'll send in is a weak coherent state, or basically a kind of classical, quasi-classical field. A in. So this is a field that would be produced by a laser. So now, A in is basically a number. It's the coherent state amplitude. Omega L is the laser frequency. So the fact that the laser is, oscillating at a rate omega L, that means if you, stuck it directly into the Hamiltonian, you get a time-dependent Hamiltonian. And there's nothing wrong with that per se, but I think more people are more comfortable. It's more convenient to solve time-independent Hamiltonians. So to get rid of that time dependence, what you can do is you can apply unitary transformation, where you transform sigma Eg to sigma Eg e to the I omega LT. So if you want, you can say that you're going into a frame that's rotating with the laser frequency. And so I'll just leave, I'll state as a claim that when you do that, your total Hamiltonian for the Maxwell-Bloch equations sorry, just to have more room. So I'll just write out everything in full to avoid confusion. So there's this detuning delta, where delta is defined to be the difference between the laser frequency and the atomic resonance frequency, minus I gamma 1D over 2 minus I gamma prime over 2. Sigma EE I minus I gamma 1D sigma EG I sigma GEJ. So this is the kind of photon-mediated spin interaction. And then our drive now becomes time independent. So the form of the drive is that any atom I can be excited by the input field. Or de-excited. Okay. So this is the now kind of time-independent Hamiltonian, including the driving fields, once I move into this kind of new frame of reference. Okay, so this is the equation that we're going to solve, and we're going to solve it in the limit of one atom, so n equals 1. So the only terms in these sums are I and j both have to equal 1. So it's straightforward to write down the full master equation solution. I won't derive it here, but it's just straightforward algebra. It's so we already solved the density matrix for a single two-level atom before. When you add in this kind of driving and the independent emission, it doesn't change. So you're just abstractly solving some 2x2 differential equation for the density matrix. And so let me just kind of write down the final solution. We'll also assume, which is sufficient for our purposes, a weak field. Okay. So the value of this input field will be much smaller than gamma 1d plus gamma prime. And that's just to say that we're only going to look in a regime where the atom is mostly in the ground state. Okay. So then, if you do that, you'll get the following equation for the atomic coherence. So rho Eg is the trace of sigma GE times rho. And the claim is that the solution is given by this, where gamma here I define as the total decay rate. So gamma 1d plus gamma prime would be the total decay rate of a single atom. Okay. So you can kind of appreciate that the denominator here as a function of delta, so as a function of my laser frequency, the structure of the denominator starts to look like a complex Lorentzian. Right, so if you shine light in on resonance, if delta is 0, then the atomic response to the atomic coherence you generate is the largest. And as you detune the laser more and more from the atomic resonance frequency, so as delta gets very large, this atomic coherence goes to 0. Okay, so this solution knows that there is an atomic resonance that the laser is trying to hit. So this equation here is a little bit abstract, but it becomes a little more physical when we go back and try to calculate the field's properties. Okay? And in particular, we can define, so imagine we have a single atom and it's sitting at z equals 0. So then what I can do is I can use this wave equation here and evaluate the field on both sides of the atom. Okay, so I can calculate the field A at z equals 0 plus. Physically, that's like the transmitted field. And I can compare that to the field at z equals 0 minus, which is just the field that I send in. Yep.
in a general n case, we'll have like there's that term like within that like ij sum, which is like sigma eg like sigma g. So then like within there like we're assuming that the overlap of like ground states of kind of like ground states of like neighboring particles is like in general non-zero. That's why like this term does not simplify further, or because like the sigma eg from what I remember was something like a cat e bra g or something.
Right.
And then like those guys would, if they're on different sides, that thing should be 0 if the overlap of the wave functions is 0, right? But we're not assuming that, I understand.
Oh, okay, right. So if I were to go and literally try to solve with n atoms, right, my Hilbert space in general will be 2 to the n. So I have one single wave function for the entire system. It doesn't separate in general. And so your wave function would have coherences between atom I and atom j. And that makes the problem potentially non-trivial. I'm not sure if that's what you're asking.
No, sure, I see. We just cannot decompose it into like single particle wave functions and then like.
No, so you could try it, and so I mean it's maybe kind of embarrassing to say, but we quantum opticians are not very sophisticated in terms of mathematical. I mean the range of techniques we've developed for many atom problems is quite limited. So in practice, one of the main things that people do when you have many atoms is to do mean fields, but that doesn't justify that it's correct per se. It's just more a statement that we don't really know how to deal with the many-body problem.
Okay, cool, thanks.
What? Wait, did you have a question? Or? Okay. Any other questions?
Just a question about this weak field approximation that we are working on. Does it imply that in the general case we would have a coherence more complex? It's leading to a simplification at that level, right?
Right. So in general, what happens is if you allow for a strong field, so here, weak field, you can basically say that there's a linear relationship between the fields and the atomic excitation. So you double the field intensity, you double the amount of population. But in general, since it's a two-level system, that can't be true forever. So at some point, when you come in with enough photons, your atomic population has to saturate, even if you keep cranking up the field more and more. So yeah, like in general, you'll have kind of nonlinear corrections. So if you were to expand as a polynomial in the driving, you'd have nonlinear corrections to this result here.
Thank you.
Yeah, so if you want another way to say this, what I write down here, I'm only going to be interested in the linear transmission coefficient. Okay, so procedurally, the way to calculate the field going past the atom is okay, yeah, so the notation is this equation here is still completely general. So I can have any number of atoms, and I and j can go from 1 to n. And then only here am I restricting to just one atom. So in particular, if I only have one atom, then actually this term disappears completely. Okay, so procedurally, the way to calculate the transmitted field is straightforward. I already solved for the expectation value of sigma GE. And then if I want to calculate the total field, I just have to take the expectation value of this entire thing. I know the field that I send in. In that equation, I calculate the expectation value of sigma GE. So then I can just go and write down the transmitted field. So I'll skip the algebra, but I'll just give the result. So then what you find is that A of z equals 0 plus. You can define as a frequency-dependent transmission coefficient times A of z equals 0 minus. And that transmission coefficient is defined as gamma prime minus gamma 1D minus 2I delta over the total gamma minus 2I delta. Okay. So that's just the kind of formal result. Let me just draw it out so that it makes more intuitive sense. So pictorially, let's take the realistic regime where gamma 1D is much smaller than gamma prime. So that's the realistic case. So if you have an excited atom, it only emits into your Gaussian beam a few % of the time, whereas most of the time it's actually lost. So in that case, what you can do is you can plot, as a function of detuning, the total transmission, or this total transmittance. So the baseline would be 1. And then what this formula predicts is that you get a Lorentzian response. Okay, so if you're far away from resonance, your atom doesn't respond to the field, your transmission is 1. And then on resonance, the atom actually attenuates a little bit of light. So physically what it does is it absorbs a photon from your Gaussian beam, rescatters it into other directions, and so then the transmission in the Gaussian beam is reduced. And the amount that it's reduced is 4 gamma 1D over gamma, approximately. You can also look at the transmission phase shift as a function of delta. So let's look at the angle of t. So remember when we had a pure chiral waveguide, this phase shift could be very big. It could be on the order of pi. But now, because you have this kind of large free space emission, your coupling efficiency of the atom to your Gaussian beam is dramatically reduced. And so there you find that the maximum phase shift, so the phase shift is always close to 0. But the kind of maximum phase shift you pick up is also on the order of gamma 1D over gamma. Okay. So in other words, if you had a 1% coupling efficiency of the light, the maximum phase shift that the atom can provide for near resonant light is on the order of 0.01 radians. Okay. Another thing you can look at, which will be relevant a bit later, is you can look at the tails. So you can say, well, so this is now so far I talked about the maximum response on resonance. You can ask what happens if I go into the tails. So if you go into the tails, then what you can find is that the phase shift, obviously it goes towards 0, but it goes towards 0 as it scales like kind of 1 over detuning. Sorry, 1 over delta. Whereas if you look at the attenuation, that goes like 1 over delta squared. Okay, so what that says is that as you go away from resonance, of course, your atomic response decreases, but even though it decreases, your atom still continues to provide a little bit of phase shift for light, whereas the kind of the amount of transmission very quickly goes to 1. So your atom becomes dispersive rather than absorptive. Right? If you're a little bit familiar with quantum optics or atomic physics, this is also the kind of basis between atom trapping with laser light. So when you really try to trap an atom or create an optical lattice with lasers, what you do is you take a laser field, you give it a very large intensity, but you go way off resonance. Okay? And then the way that the atoms are trapped is because they continue to see this kind of phase shift, while the amount of kind of absorption or scattering of light really decreases significantly. Okay? So the kind of take-home message is that, which will become important a little bit later, is that at large detuning, the atom mostly becomes dispersive. Yep. Yep. Yeah, well, you can kind of see it visually. So mathematically, let me try to draw in the complex plane what's happening. So on resonance, so at delta equals 0, let's define our input phase or input beam to be, real. So to have a phase of 0. So generically, when you drive any resonator on resonance, it'll respond 90 degrees out of phase. So then you expect rho GE to be 90 degrees out of phase. And then it's also generically true that when you have a dipole that's emitting light, the light that's emitted will be another 90 degrees out of phase. So the kind of re-radiated field will be 90 degrees out. And so if it's a chiral situation, what you know is that the sum of the input and scattered has to be of magnitude 1, right? Because you can't lose the light. So in this case, the A scattered is actually kind of twice as big as A in and pointing in the opposite direction. That's why you get this kind of magical pi phase shift in the total field. So what happens here when gamma 1D or the coupling efficiency becomes very small is that this A scattered actually becomes very short. And so your total field is still A in, just with a little bit of amplitude reduction. And so the phase that you get on resonance is 0, and then the total field, its amplitude is shrinking. Yeah. So the chiral is just this kind of magical. The purely chiral case with no absorption is this just kind of magical case. Any other? Yep.
So a little bit related to that previous question. In the case where we just had the pure chiral waveguide, the atom maybe absorbs the light, but then retransmits it in a discrete single direction.
Right.
But here we are adding this extra radiance in all the seroradiance.
Right.
And then the forward direction, which is where we have our detector, would be like a set of measures 0 almost, or infinitesimally small compared to the rest. Is this like an okay in the model, or is this where things break down?
Oh, okay, right. So, in the 3D case, when I say the forward direction, it's not like a singular point. So I'm not literally looking, on this point here. So when I say, the total field or A, this actually refers to this entire Gaussian mode. So it's not so in that sense, that's why it's not like an infinitesimal object. And so maybe if you want to say it more properly, like you can say that when I have a set of electromagnetic modes, I can define a basis. So the usual basis you take is plane waves, e to the I kz. But you're also free to take a basis where one basis vector is just the Gaussian mode. And then you have a set of orthogonal basis vectors. And so one way you can view this AZ is that you can view it as the projection or the overlap of the total electromagnetic field into all modes, but only then kind of projected into this one discrete Gaussian mode. So one nice thing about this kind of chiral structure, again, is that you're not really allowed to have back propagation. Okay, so even though I just solved for the transmission coefficient of a single atom, I can immediately write down the transmission for n atoms. Okay, so in particular, for n atoms, I have the composite transmission coefficient going through the entire system has to be just that of a single atom taken to the nth power. So then what I can also look at is I can look at the transmittance. So what's the fraction of energy that's transmitted through an n-atom system? That's the complex transmission coefficient squared. And then in the regime of weak coupling efficiency, when you exponentiate this thing on resonance, the only case I'll really care about is on resonance. Okay, so let's take delta equals 0. Then when you exponentiate this thing to the nth power, you can more or less approximately write it as an exponential itself. So e to the minus 4 times atom number times gamma 1d over total gamma. And this you can define as e to the minus d. Okay? So this d here is known as the optical depth of my medium. So in quantum optics, or atomic physics, people always talk about the optical depth of your ensemble. And then in our to relate it to our toy model, it's just proportional to the atom number and to the coupling efficiency of a single atom, gamma 1d over gamma. And so this is now a quantity. So this provides a way for you to map our mathematical toy model onto a real experiment. So in a real experiment, you just shine light in on resonance, which is weak. You try to measure the Beer-Lambert law of how much light is attenuated on resonance, and that gives you the optical depth. Yep.
Sorry, the last term in the last term you had a factor that is the gamma 1d over the gamma.
Right.
And my question is, there is any relation between this factor and the factor that you showed the last section in your presentations? Because you were defining an efficiency of the waveguide transmission, right? So.
So I'm not sure which equation.
Thank you. It was not an equation in your presentation. It was just a fact that you show us when you show the comparison between two different waveguides.
Oh, okay, yeah. Yeah, I'm sorry. So there's only two independent decay rates. So there's the emission rate of a single atom into either the chiral waveguide or this Gaussian mode. And then gamma prime is the emission rate into everything else. So gamma is just the total of those two. And then, at least in free space, gamma prime is much larger than gamma. So if you want, this is also approximately equal to 4 times n times gamma 1d over gamma prime. And so, yeah, now if you want to relate it to true waveguide QED, I mentioned that for a single atom, this gamma 1d over gamma prime is like a few percent in a nanofiber, about 50% in a photonic crystal, and it's close to, well, it's much bigger than 1 for like a superconducting circuit. And then to compare, in realistic atomic ensembles, this gamma 1d over gamma prime could be something like, actually very small, 10 to the minus 3, 10 to the minus 4. Huh? Okay. Sorry, maybe one more thing to mention is this you can also, it's not completely obvious, but you can also geometrically relate it to actually the first thing I introduced in my lectures. So this thing is also approximately equal, I mean, up to some coefficient. It's also the number of atoms times the resonant wavelength squared divided by the beam area. Okay. So I said that before, the way to understand efficiency is just to realize that a single atom on resonance has a cross-section, scattering cross-section that's given by lambda squared. So all these results here are equivalent to that. Okay, so what this result says is simply like even though one atom has a very weak response, when you have enough atoms, eventually the photon you send in is going to scatter off one of your atoms. And in this case, you see that the form of the scattering is not particularly coherent. It just your photon disappears, right? Because it scatters into 4 pi. Okay, so that's obviously not a useful application, right? Like if you want a photon to disappear, you don't need fancy atoms to make that happen. But what I'll show now is that this same figure of merit, this optical depth, which in a 2-level medium just describes how likely you are to lose a photon. It also is a figure of merit once you try to functionalize the atoms. So if I try to do something fancier with the atoms, something kind of more coherent, more quantum useful, this optical depth will still show up in that context. Okay. So that gets to our first application, concrete application of quantum optics. Which is a quantum memory for light. And there's a specific, so a quantum memory is just a general goal or objective. There's different protocols to realize a quantum memory. And the one I'm going to talk about is EIT, or electromagnetically induced transparency. So let me state the kind of goal of this application. So if you want to transfer quantum information over long distances, I think it's pretty clear that the photon is the most realistic way to do so. So for example, you might have photon qubits. So you have a single photon, and you might have the qubit information is stored in polarization degrees of freedom, so left polarization, right polarization, or anything you want. So the point is that this photon, if you send it through an optical fiber, it can actually propagate a long distance without loss, several kilometers, tens of kilometers, etc. So it's a good way for propagating quantum information, transferring quantum information over long distances rapidly. But it's not but it doesn't live a long time. So it propagates far, but it propagates very quickly. And so the time it takes, so even though it propagates tens of kilometers in a fiber, the amount of time that it physically lives is actually quite small. Okay, so if you want to kind of keep that information for longer, you have to. Yep.
I don't exactly see what do you mean by left and right polarization in this case, because I understand this will be a quantum state, and then we'll have say a certain a 2-dimensional type of vector, right, which is going to point us in a certain direction.
Qubit. Yep.
And then this thing will encode us the single qubit, single logical qubit information, right?
Yes.
But then what is left and right then?
Sorry, it could be left circularly polarized, right circularly polarized, or X polarization, Y polarization. So these are two states of light that are orthogonal to one another.
Oh, I see. I see. So circularly polarized, it will be more it's about the time dependence of that, like what happens with that vector as it evolves.
Exactly, yeah.
Okay, sure,
Yeah.
sure, thanks.
So it's a fair qubit in the sense that we know how to manipulate polarization to switch from one to another. We can beam split. We can have selective polarization beam splitters. So then we can take a zero logical qubit and then do something with it, etc. So it's not the only way to encode qubits into photons. It's just kind of a paradigmatic example. Okay, so they propagate far. But live a short time. So if you imagine hypothetically, we one day has some massive quantum computer where we're trying to, we want to decide some order in which we can implement quantum circuits and gates. We want that we can kind of store a lot of these qubits and then kind of retrieve them when we want just to do the operation. Okay. So the fact that photons and fibers live a very short time isn't a scalable solution, and so what you would then like to do is find some unitary map where you can take these photons, you send them into atomic medium, you generate an atomic, so the atoms absorb that photon, but hopefully in some coherent way, and then by the virtue of the fact that it's a unitary map, you can then also kind of undo the process later. So the end goal is somehow to kind of get these two orthogonal photon states to get absorbed into two orthogonal atomic collective excitation states, right? And then hopefully these atomic excitations will live for much longer than photons can. Okay, so that's the goal.
Those photon states are like so short-lived. Like photons do not interact much with the environment, so.
Yeah, so I should be able to do the math offhand, but I can't. So you can take, so what is known is you can measure the amount of attenuation a fiber has, and so a photon might propagate 10 kilometers or 100 kilometers. But it does so at the speed of light. So then the maximum lifetime, if you just try to store a photon in a fiber, is 100 kilometers, divided by the speed of light, which is just, what was it, like microseconds or something? So that's really the issue.
Okay, I see.
Okay, so EIT is just one particular way to implement what I drew here, and the way that EIT works is simply utilizing more realistic atomic structure. So I said my minimal model of an atom before is one ground state, one excited state, and I won't get into the details of the atomic physics, but actually most of the time, if atoms have nuclear spin, etc., you can actually have an entire ground state manifold. So for example, a realistic atom so any of the species that people most commonly use in the lab, you would have a ground state and excited state. This is the same ground and excited state that I mentioned before. But then you might also have a third state, which I'll call S, which also lives in a ground state manifold. So these could be like different Zeeman levels of your atom, or different hyperfine levels. So effectively, these two states, this state also lives forever. And so then the scheme is the following. So we'll send in kind of quantum light on this transition. Sorry, let me draw it more clearly. So we could, for example, shine in single photons or a weak coherent state on this transition. These photons will have a detuning delta, which is exactly the same delta as what I showed there. Okay, so up to now, this type of two-level atom interacting with light is exactly what I presented before. The only difference now is we have this one other state. Okay? And what you can do is you can then use a classical control field, a classical laser. Which is resonant with the S to E transition. And it'll just be described by, it'll be characterized by some classical Rabi frequency omega c of t. So this laser, the goal is just to kind of try to induce transitions from the excited state to the state S, or induce oscillations at a fixed rate. So it's just a classical laser whose intensity you can tune up and down by hand.
What is the importance to have a classical laser to do that transition, not a quantum one?
So practically, it's a classical. So this is just going to be in practice some field with a giant amplitude. So a classical laser is sufficient because so basically, this quantum memory is like is a passive operation, in the sense that ideally, so it doesn't generate any entanglement or extra additional quantumness beyond what you sent me in the first place. So example, you send me some photon qubits. My job is just to store it for you and give it back to you. Okay, so there's nothing quantum I'm looking for in this application. In that sense, you can imagine it's sufficient to send in a classical laser. You could ask, what if I had a quantum field acting on this transition rather than a classical one? And so then there actually are a couple of specific protocols where that could actually lead to interesting quantum states of light, where you send in now a classical state on this transition here, and then the system spits back at you a quantum state of light. So that is possible. There are at least a couple of paradigms to do that. But here, because we're just interested in this kind of passive operation on qubits, a classical laser is sufficient.
Thanks.
Any other questions? Okay. So pictorially, the goal, I think you can maybe already see. So the idea is, imagine I send in a photon. That photon might take one atom from the ground to excited state. Since the atom is excited, it would just want to re-emit that photon immediately. But what you can do is essentially use the classical field to induce a Raman transition. So your single photon brings an atom up to E. You try to use this classical laser to kind of transfer it coherently down to state S, and since state S is a ground state, it'll live, forever, or at least a very long time, and that's going to constitute your quantum memory. So the idea is simple, and then the main kind of thing to analyze is really how well does that work in practice. All right, you give me a photon in real life, and can I give it back to you 20% of the time, 90% of the time, 99% of the time? And what's the physics that dictates that? Okay, so let me now write down the effective Hamiltonian for this new EIT configuration. And just like before, so sorry. Let's also deal with just a single atom. What we learned kind of from experience is that because it's still a chiral waveguide model, if I want to know the response of n atoms, I just have to take the response of one atom and exponentiate it. Okay. So for completeness, let me just write down the effective Hamiltonian. So for a single atom, I have emission into the wave, or into my waveguide, or into my Gaussian beam, plus my additional free space emission gamma prime. So I've gone into a rotating frame. So I shine in. I imagine shining a photon of a given frequency, omega L, and I define this detuning delta, which is the difference between my laser frequency or my photon frequency and this transition here. And then once I go into this kind of rotating frame, the energy level of state S is going to change as well. Okay, so it's just a global shift of what I'm calling zero energy. Yep.
Because I thought this G is a ground state, and so that's the first question. And second question is like, when we have this like Rabi frequency and so, right? Like, is it that we need to, because like if we kept like having this laser just being on, then like we would like translate the population from like S to E and back. And so on.
Yep.
So we need to fix the pulse, right? Like to a certain shorter period of time, such that we only translate down, right?
Yeah, so
Okay.
I'll get to that. Right, so you do want to make the control field time dependent, which is basically to say that once it's down in S, you want to kind of shut it off.
Oh, I see.
And I'll get into the physics of that later. As far as like what is this state physically, so without getting into a complicated discussion of real atoms and hyperfine structure, maybe the believable argument. Well, let me try to put it as a minimum argument, and you can tell me whether you believe it or not. So even if I go back to hydrogen, my ground state is in principle twofold degenerate because I have the electron spin, right? I can have up and down. Now, photons at this level of discussion, so photons only couple to lowest order to orbital degrees of freedom and not spin. So the fact that I have this kind of second ground state there doesn't actually do anything. But now if I allow for more complicated physics, so if I allow for spin-orbit coupling, and then I allow for nuclear spin and hyperfine interactions, then maybe it's plausible that that second ground state, which is decoupled in hydrogen to lowest order, now actually becomes optically accessible through light itself. So maybe that's the kind of minimal story of where these extra levels ground. So it could be effectively a true ground state, but just coming from additional interactions that I didn't really talk about explicitly.
I see. And this other ground state, like, is it going to be still degenerate in energy with like the original one we excited from? It's just like one is optically addressable and the other one is not, or?
It could be the same. It could not. It doesn't really change the physics.
Okay. The point is that it's metastable, at least.
Yes. Yeah.
Okay.
So depending on how you say it, like it could be another true ground state. So it could be two Zeeman levels within the true ground state manifold. So then they would be exactly degenerate unless you applied magnetic fields to kind of tilt them to have an energy difference. They could have there could be a slight energy difference because it's coming from like just hyperfine. So this could be a hyperfine excited state, but still within the ground state manifold. So this would have typically a energy separation of a few gigahertz.
Okay.
So which means that in principle, this thing could emit a gigahertz photon and spontaneously emit, but the lifetime of it, for the time scale of that to happen is kind of infinite. So effectively, it's a ground state.
Okay, perfect, thanks.
Yep. Okay, so two of these terms are exactly the same as before. So this term here and this term here are exactly the same as what you have for a single atom coupled to a chiral waveguide or to a Gaussian mode. And then when you have this third level, the new terms are this, which are pretty easy to understand. This term here just describes the energy of the state S. And then this term here describes the classical driving. So the classical field can induce transitions, so the state S would go to E or vice versa, so Rabi oscillations. Okay. Because it's a single atom, there's 3 possible states. Your density matrix is 3 by 3. You could go in principle solve the master equation. Okay, so it's not hard, but I'm not going to do the steps explicitly. So let me just kind of claim that if you solve the density matrix equation, and again we'll take the weak field limit. You obtain the following modified atomic coherence. Okay. So this equation is pretty abstract. I don't expect you to kind of get anything out of it per se. Let me just point out 2 limits though. So if my control field is set to 0, then I get the same result as before of a 2-level atom. And that's just to say, if I don't even turn on this control field, there's no way that this state S could ever get populated. So then this answer, which I wrote down here, reduces to this answer that I previously gave. Right? The more interesting case, though, is if my control field is turned on, and I'm at 0 detuning. Okay, so I shine in a laser exactly on this G to E resonance. You notice that there's this kind of factor of detuning up in the numerator. Then what you find is actually there's no coherence between the ground and excited state. And then if there's kind of likewise, I didn't directly prove it, but you can imagine that the reason there's no coherence is because there's no population in excited state in the first place. So that's kind of weird, right? Because in the 2-level case, I shine in light. And if I shine in light on resonance, that's actually the most efficient way to bring population up to the excited state. Once I have population up in the excited state, it can emit a photon into 4 pi. And therefore, I can have attenuation or absorption of the light that I send in. But now, just by adding this 3rd level in this control field, I again shine in light on resonance, and I have 0 excited state population. So if the atom is not excited, it can't possibly emit a photon into other directions. And therefore, under this condition, the light that I send in has to be 100% transmitted. Okay, so that's where this name electromagnetically induced transparency comes from. So one can do the calculation more rigorously and really prove that the transmission coefficient is 1. But hopefully, I won't do that explicitly, but hopefully the kind of intuition is clear enough, right? If I don't have any excited state population, I can't possibly emit a photon into 4 pi. and therefore the photon has to have come out in my Gaussian mode. Okay, so at least on resonance, I have perfect transparency. So then you might ask, like, how the heck can that possibly happen? So it's nothing kind of, it's not a quantum effect per se, it's just a classical interference effect. If you want an analogy, just in terms of kind of classical mechanics, you can think of it as the following. So let me put a kind of classical mechanics. Analogy. So imagine I had two masses, M1 and M2, sitting on a surface. And hypothetically, let's imagine that only M2 was sitting on a rough surface. Okay, so this mass here, if it was to move, would experience friction. Okay. So now if I connect these two masses together by a spring, I can find some normal mode of motion. But clearly that normal mode of motion involves both M1 and M2 moving. Okay, so then it's clear that this normal mode would be dissipative. You get it moving at time 0, but later on you'll see that the friction has damped out the motion. So this would give you a dissipative normal mode. But now let's take the following case. So let's then have M1 and M2. So then the question is it possible to create some type of normal mode of motion that is actually frictionless? And the idea is that it should be possible as long as that normal mode does not involve any motion of M2. Okay? So for example, if I connect M2 to yet another mass, let's say M1, just to make it symmetric looking. Now if I create this kind of normal mode where M1 and M2 are moving with equal amplitude and out of phase, then the force that they impart on mass M2 completely cancel out. So then it's possible that M2 doesn't move at all. These masses M1 would oscillate forever, and that normal mode has no absorption. Okay, so now I can get no absorption via interference. In this case, when I say interference, it's the interference via the pathways in which M2 could experience a force. Okay, and so it's not obvious at all, but it turns out that the equations, if you were to write down the actual density matrix equations for electromagnetically induced transparency, they have exactly the same mathematical structure as this mechanical analogy. Here, the kind of interference is quite clear. It's an interference of pathways, because you can excite this state E coming from the ground state or coming from the state S with these two different laser fields. Yep. Yes. Not only simulate, you can even do better, which is you can turn it into something useful. So So there's a field known as optomechanics, where you essentially try to induce coherent coupling between light and a mechanical resonator, a mechanical degree of freedom. So basically like a nanoscale or microscale version of some mass on a spring. And so there is a phenomenon called optomechanically induced transparency, where exactly one of the legs, one of the degrees that you're exciting is a phonon. And then the reasoning would be kind of the same. So I have a photon, but if I can somehow create a phonon mode with a very long lifetime, then maybe I can store into the phonon mode and then get the photon coming back out later. So ideas like that have been pursued experimentally. You can also do something even fancier, which is to say that my photon, I can actually have two different types of photons that couple to the same mechanical mode. So I can have one optical photon, at visible wavelengths, for example, that couples to the mechanics. But then maybe I can make the mechanics also couple to microwave photons. So then what you could do is you could send in a microwave photon into the phonon. You can reconvert it out as an optical photon. And then you've done microwave to optical coherent conversion. So I think we're still kind of far away from actually realizing this with high fidelity, but the kind of long run perspective is that you might have a transmon qubit, which creates a microwave photon, and then all of a sudden you can link that transmon qubit through a real optical fiber to a transmon qubit kilometers away. Yeah. It works in principle, so people actually tried it, but it's massive. So because it's microwave, you need your entire waveguide to be cryogenic. And so you would need a cryogenic tube that's like, and so people have actually tried it, like with I think they've managed to create a cryogenic tube that's like tens of meters to couple, but it's a massive experiment. It's not something I'd recommend doing at home, All right, so okay, so one kind of interesting consequence of this, yeah. Yeah, so it's kind of like here, like if these two masses are identical, then it's easy to see what the normal mode is. If I change this to M3, then you can imagine that there is some new asymmetric normal mode. So it's the same story here, that there is always a normal mode to create transparency. Okay. So besides kind of creating perfect transparency, it turns out there's a lot of interesting additional optical properties. Right, because if the whole goal is to create transparency, there is an easy way to do that. Just you don't even need atoms in the first place, right? Vacuum is perfectly transparent. So the reason that EIT is interesting is not because of the transparency per se, but of a few additional properties. Okay. So to see that, now let's go to a periodic system. So let's take n going to infinity. So in the kind of chiral waveguide picture, I have a set of atoms at periodic separations, let's say some distance d. And now, again, the physical propagation problem is no harder to solve when I have 1 versus n, because, again, I just have to take my transmission coefficient and exponentiate it to the nth power. But the nice kind of conceptual thing about putting on a lattice is to say that now I can define a block band structure, okay? So in principle, my propagation is described by Bloch's theorem. And the point is that what Bloch's theorem says is that for any given detuning, sorry. So if I look at, for a fixed detuning, if I look at my total fields at a position z plus d, yes? Yeah. Exactly, yeah. Yeah, so I didn't write it. I will get to it. So the full right. So I could write down the population in state S. That turns out to be equal to omega c squared over delta squared omega EE. Okay. In this form, it's a little bit abstract. I'll later tell you what the population is in more physical terms. But yeah, so I only solved part of the density matrix, but in principle, you could write down all the components. Okay, so again, the fact that it's on a lattice doesn't change the complexity. I just keep I know the transmission of one atom, and then because my field has to keep going, I can just exponentiate this result. So the only point of this Bloch theorem is to kind of force to rewrite the solution in a certain format. So Bloch's theorem says that if I know the field at position z, then the field at position z plus d, I can formally write as e to the I k d, where k physically is my Bloch wave vector. Okay. So physically, what you do is you solve for transmission past one atom, and then transmission for another free propagation distance d, and then you just formally rewrite it as your field at position z times e to the I k d. Okay, so that defines your Bloch wave vector. So now what you can do is you can take that solution and expand it around small delta. So k of delta to lowest order is omega over c plus delta over c. We can define nz as 1 over d, which is the density of atoms. Okay, so then if I start expanding further, I'll get term proportional density times gamma 1d times delta over omega c squared plus I nz gamma 1d gamma prime delta squared over 2 omega c to the 4th plus dot dot dot. Okay. So at this stage, that doesn't really carry much physical meaning, but let me kind of explain each term in more detail. So this first term here is just free propagation. So even if I had 0 atoms or 0 atomic density, this just describes the fact that light propagates with a dispersion relation k equals omega over c. So this green thing here is just equivalent to k equals omega over c, so free propagation. It's not very interesting. The term that's proportional in delta gives me my group velocity. Okay, so so this term here I can use to evaluate my group velocity, which is dk d delta, or the inverse of that. And then when you do that calculation, you see that your group velocity depends on the control field intensity itself. Okay, so my medium is transparent to lowest order, but when I send a pulse through, I can dramatically slow down that pulse or speed it up by playing with my control field intensity. So it depends on control field intensity. So that sounds kind of cool. It's kind of abstract, but my claim is that in real experiments, this thing is much less than the speed of light. Okay, so in practice, when you do this EIT, your pulse will be probably very slow. You can ask how slow. So the first time that people did EIT in a Bose-Einstein condensate, they slowed down the speed of light, or in this medium, to something like 17 meters per second. And then it was published in Nature, and then the cover of that Nature was like a cartoon of someone on a bicycle racing a pulse of light. Okay, so that seems kind of cool. And then let's look at this last term here. And you notice that it's imaginary. So if I had a purely real block dispersion relation, so if k as a function of delta is purely real, that describes your kind of normal block band structure. You get a normal dispersion relation. The fact that it's imaginary tells you that now your dispersion has some absorption associated with it. Okay? So you see that when delta is 0, then this imaginary term disappears. That reproduces the perfect transparency. But what this result says is if you're not working exactly on resonance, if you detune your input field by just a little bit, now it starts to absorb. Okay. So you can calculate that absorption. What you find is that when you transmit through an ensemble of n atoms, so again, what this result says is that you'll get as long as you're not exactly on resonance, you'll get an exponential attenuation that's proportional to the number of atoms you propagate through. Okay. So maybe now is a good time. So these results at the moment still, I think, look a little bit abstract. I'll kind of try to relate them later on to tell you how quantum memory works and how well it works. So maybe now, now's a good time for a break, and I'll explain that when we come back. But are there any questions on this part? Sorry?
Related to these periodic atoms, right?
Mm-hmm.
Like in the lab, would the normal way of realizing this include like another optical trap? And if that's the case, how do you make sure that those lasers don't interfere with the one that you're trying to observe the propagation?
Yeah, oh, I'm sorry, I should have explained better. So you don't need periodic atoms. So in real EIT, the atoms are completely random. So in that case, you could also just describe, so mathematically, you just have to take this transmission coefficient to the nth power. So it doesn't depend on order or disorder per se. So yeah, the only reason I do this is it makes, well, yeah, so the end result of everything I'm saying is independent of order or disorder. I just find that this kind of Bloch's theorem helps you to kind of better visualize the physics of EIT and eventually how this quantum memory works. So it's more a mathematical trick rather than an actual necessity.
Usually in the lab, we use two beams to make the electromagnetic induced transparency. The test field and the another one. But here in the equations, I don't see two frequencies. And can you explain more, please?
Yeah, so there are. So visually, like, I mean, we have one field that's on this G to E transition. I label that by AN, so that would be my probe or my kind of test fields. And then I have this control field that's driving the E to S transition, which I describe by omega C. So here, I mean, so probably the issue is like, again, I'm trying to calculate EIT, but in this kind of hybrid language of chiral waveguide QED. So I think maybe for that reason, the variables and so on look a little bit different than what you're used to. But everything is exactly the same. So here, the two fields are this AN and omega C.
Okay.
And now you see that the coherence depends on the two together.
Okay, there's one more question. The interactions between the beams and the atomic medium and can be the cancellation of the absorption of the field of proof and modifying the index refraction, okay? And promoting the phenomenal called slow light. We can see the slow light here too.
Yeah, so it's in this kind of, so when I calculated the group velocity, you see that the group velocity depends on your control field's intensity. So at this moment, it's just an abstract quantity. You'd have to kind of put in numbers, what's a realistic atomic density, et cetera, to actually get a physical number. But my claim is that if you do put in realistic numbers, this group velocity would be much smaller than the speed of light. So I mentioned this experiment where in a BC, people created this group velocity that was 17 meters per second. That's encoded in this equation here.
Thanks.
More questions? Okay, so let's have a break.